Hello, and welcome to Sleep Gravity. After the 1991 eruption of Pinatubo, the skies in many places on Earth took on unusual colors. Late afternoons could appear deeper red, more violet, and more prolonged, as if sunlight had to pass through something extremely thin before reaching human eyes. No roof appeared overhead, no dark curtain fell over the ground. Day still arrived, night still descended, the seas still moved, and clouds still drifted across the continents. But very high in the atmosphere, tiny particles born after the eruption had begun to change the path of light. The heavy ash from a volcano does not remain in the sky forever. Most of the larger particles fall back down, are pulled to the ground by rain, or leave the air in a relatively short time. But not everything a volcano sends upward behaves like ash. In a powerful enough eruption, sulfur dioxide gas can rise above the familiar layers of air where everyday weather takes place. When it reaches the stratosphere, a higher and more stable region of the atmosphere, that gas can transform into extremely small, light-colored sulfate particles, so light that they can remain suspended for a long time. They do not turn the sky black. They do not block the sun like a wall. They simply scatter part of the light, sending a very small portion back into space, making the sunlight that reaches the surface a little softer for a period of time. A change that small may sound insignificant, but Earth does not receive light at a single point. The oceans, forests, deserts, ice, snow, clouds, and atmosphere all take part in receiving and returning light. When tiny particles spread across a wide region of sky, then continue to move around the planet with high-altitude winds, a very small fraction of each sunbeam can add up to a trace large enough for instruments to measure. After Pinatubo, that trace appeared in satellite data, in the haziness of the stratosphere, in the amount of light being scattered, and in the temporary softening of global surface temperatures. Those tiny particles belong to a much larger family of particles suspended in the atmosphere. Some come from the ocean, when waves break apart and send very small salt crystals into the air. Some come from deserts, when wind lifts mineral dust from dry ground. Some come from wildfires, from smoke, from ash, from human activity, and from natural processes that take place every day on a living planet. Some light-colored particles tend to reflect sunlight. Some dark particles absorb light and warm the air around them. Some particles do not block much sunlight by themselves, but become footholds where water vapor can gather, gradually forming tiny cloud droplets. They are all small particles in the sky, but each kind meets light in a different way. Sunlight travels through space in silence. Before it touches the ocean's surface, a leaf, or a rooftop, that light must pass through the thin layer of atmosphere wrapped around Earth. From the ground, the sky seems endlessly high. From outer space, the entire atmosphere looks only like a faint blue rim, almost impossibly thin, lying between the living world and the vast darkness beyond. Within that rim, light is constantly divided into many different fates. Some passes through and warms the surface. Some is returned by white clouds. Some meets ice and snow, then bounces back into space. Some touches dark particles and is held in the air. Some strikes extremely small bright particles, changes direction, spreads outward, and no longer travels straight down to the ground as it first did. The shade made by tiny particles is not like the shade of a tree canopy or an awning. There is no clear edge where it begins. There is no obvious dark patch spread across the ground. It is thinner than mist, more scattered than cloud, changing with the wind, with altitude, with season, with eruptions, with salt spray from the sea, and mineral dust from deserts. But when it exists on a large enough scale, that layer of particles can soften the light of an entire planet slightly. Earth does not need a giant roof to receive less sunlight. Sometimes, a layer of extremely small particles suspended high in the atmosphere is enough to leave a subtle trace in the climate system. The beauty of sunsets after a volcanic eruption is not simply in their brilliance. That deeper red is light that has passed through an unusual atmosphere. The long streaks of violet and orange across the clouds are signs of tiny particles scattering light in a way that an ordinary sky does not do so strongly. A person standing on the ground may only feel that the sky looks strangely beautiful that day. A satellite above can read the change in the thin layer of particles surrounding the planet. Those two perspectives meet in the same place. Light has been redirected before reaching human eyes. And yet, a dimmer sky does not mean a healthier sky. Some particles can reflect light and soften temperatures for a time, but many particles in the air can harm the lungs, dirty the sky, alter clouds, affect rainfall, and leave behind unwanted consequences. A dirty pane of glass may make sunlight feel less harsh, but softer light does not make the glass clean. The atmosphere is similar. Weakening part of the sunlight is not the same as healing the climate, because climate is not only temperature. Climate is also water, wind, rain, seasons, crops, ice, forests, oceans, and the deeply interwoven connections among them. Pinatubo left behind a quiet lesson about Earth's sensitivity. An eruption in one mountain region can send material high into the air, allow atmospheric currents to carry it far away, and then change the amount of light reaching many places around the world. A single, tiny, nearly invisible particle cannot cool the planet, but countless tiny particles in the right layer of the atmosphere, with the right reflective properties, can make Earth's surface temporarily gentler. That power does not come from their size. It comes from their position along the path of light. From outer space, Earth still turns slowly in the dark, lit by the sun on one half of its sphere and covered by night on the other. Between that light and darkness lies the thin atmosphere, where tiny particles drift in silence. They have no shape that humans can easily remember, no sound that humans can recognize, no clear outline like clouds or storms, but they stand in the place every ray of sunlight must pass through before it touches the sea, the land, the trees, and life. In that silence, tiny dust-like particles reveal something very large. Sometimes, an entire planet can change because of things almost impossible to see. From orbit, Earth does not appear as an object silently receiving light. The blue planet shines in its own way. Bands of white cloud reflect sunlight, like thin silk stretched across the oceans. The ice at the poles throws back a cold, pale brightness. Deserts hold a bright yellow color beneath the sun, while the deep ocean lies below in darker blue, absorbing more and reflecting less. On the same planet, light does not have one single fate. Every region of land, every cloud, every surface of water, every sheet of ice, and every tiny particle in the atmosphere changes the path of light slightly. The sun is very far away, but energy from the sun reaches Earth continuously. That stream of light travels through empty space in silence, touches the atmosphere, and then begins to branch. Some rays pass through clear sky and fall onto the ocean surface, warming the upper layer of water very gently. Some meet white clouds and are reflected back into space before ever touching the ground. Some fall onto snow, bounce away from the bright surface, and leave the planet again. Some travel deeper, meeting dark soil, dense forests, rooftops, mountain rock, and pavement, then turn into warmth. From countless small encounters like these, Earth determines how much energy stays and how much returns to the darkness beyond. Climate, then, does not begin with the number on a thermometer. Before the ground becomes warmer or colder, light has already passed through a chain of natural choices to be kept or returned, to move straight down to the surface or be deflected, to touch cloud, ice, sea, land, or dissolve into a layer of very small particles suspended in the air. Earth is not only warmed by the Sunday, Earth is also constantly answering the sun with its own brightness. A darker planet usually holds on to more energy. A brighter planet usually returns more light. This can be felt through very familiar images, without any formula. A black road under the noon sun becomes hotter than a white wall. A fresh blanket of snow makes the whole landscape shine. A day with low clouds is often gentler than a cloudless day. because so much sunlight is reflected before it can reach the ground. But on the scale of a planet, that difference no longer belongs to a single road, a single field, or a single afternoon. It spreads across oceans, continents, polar regions, cloud layers, and the entire thin atmosphere surrounding the living world. When seen from the ground, the sky seems high and empty. Clouds drift above, birds pass through, light falls downward, and the air appears transparent. But that transparent layer is not empty at all. It contains water vapor, gas molecules, tiny water droplets, sea salt particles, mineral dust from deserts, fine smoke from fire, very small ash from volcanoes, and countless other particles light enough for the wind to carry them very far. Sunlight must pass through all of these things before it becomes warmth on the skin, glitter on the waves, or the shadow of a tree printed on the ground. Some days, the sky is a deep blue, giving people the feeling that the air is clean and high. Some days, the sky is pale white, the light softer, but the horizon more blurred. Some sunsets burn red when sunlight travels through a longer stretch of atmosphere and meets more tiny particles on its way to human eyes. These differences are not only colors, they are traces of light after the atmosphere has shaped it. The sky is not a backdrop painted blue. The sky is the result of light being scattered, reflected, absorbed, and softened by a very thin layer of matter that is always in motion. In places with many white clouds, Earth appears brighter when seen from space. Clouds are like soft mirrors, not flat, not hard, not glaring like metal, but white enough to send a large portion of sunlight back. In places with dark oceans, light is more easily held, especially when the sun is high and shining directly down onto the water. In places covered widely by ice and snow, the planet seems to wear an added layer of brightness, causing many rays of sunlight to leave before they become heat. When ice melts and reveals darker ocean or rock beneath, the same amount of incoming sunlight can leave behind more warmth. A change in surface color, simple as it may seem at first glance, can alter the way a vast region receives energy from the sunday. But the surface is not the only place where light changes direction. Just above the surface, inside the atmosphere, tiny particles are also taking part in this exchange. A light-colored particle can scatter sunlight in many directions, keeping some of it from traveling straight down to the ground. A dark particle can absorb light and warm the layer of air around it. A sea salt particle can become a foothold where water vapor gathers, helping to form a cloud droplet. A very small sulfate particle, high in the atmosphere, can remain there longer and reflect light across a region of sky far larger than its actual size. These particles are so small that they nearly disappear from human sight, yet their position lies directly along the path every ray of sunlight must travel. This smallness can easily mislead the senses. A speck of dust on a fingertip cannot change Earth. A thin streak of smoke in the air also seems far too weak against the whole sky. But the atmosphere does not operate through isolated particles. The ocean can send countless tiny salt crystals upward when waves break. Deserts can carry mineral dust across entire oceans when winds are strong enough. A large fire can push fine smoke into the sky for many days. A powerful enough volcanic eruption can send material into higher layers where particles last longer, spread farther, and meet sunlight across a wider range. When these small things add together, the sky is no longer as completely transparent as it first appears. There is a very important difference between shade on the ground and shade in the atmosphere. The shade of a roof has a clear edge. The shade of a tree canopy can be seen on the ground. The shade of a large cloud can pass over a field like a slow-moving dark patch. But the shade made by tiny particles in the atmosphere has no easily recognizable shape. It does not fall as a black mass. It only weakens the light a little, scatters it a little, changes its color a little, nudges it a little away from its original path. When that very small change occurs over a wide area, the planet can sense it in ways more subtle than human eyes can. In surface temperature, in cloud brightness, in atmospheric clarity, in the color of the sky at sunset, and in the amount of light recorded by satellites from above. Earth, in this way, is like a world breathing in light. When clouds grow thicker, the planet becomes brighter in those regions. When ice retreats, some areas hold more heat. When dust hangs in the air, the path of sunlight changes. When greenhouse gases hold onto heat, escaping from the ground, the balance shifts in another direction. No single factor stands alone like one master control switch. Clouds, ice, oceans, dust, water vapor, gases, and surfaces continually influence one another. The cooling or warming of the planet does not come from one simple cause, but from the sum of countless small exchanges between Earth and light. What makes atmospheric dust particles so special is that they sit exactly on the boundary between the small and the large. They are as tiny as nearly invisible points, yet they exist within a layer that surrounds the entire planet. They are light enough to drift with the wind, yet real enough for light to encounter them. They do not look as majestic as volcanoes, but after a major eruption, it is the light-colored particles high in the atmosphere that can soften sunlight for many months. They do not have the gentle form of clouds, but many cloud droplets need a tiny particle in order to begin forming. In this way, matter that is almost invisible in the air can enter processes far larger than its own size. When light touches Earth, it does more than brighten the day. It opens a whole chain of slow reactions. The ocean surface warms, water vapor rises, air begins to move, clouds form, ice reflects sunlight, soil holds heat, plants photosynthesize. The atmosphere holds on to some warmth and allows the rest to escape into space. Tiny particles in the air sit between many steps in that chain. At times, they scatter light. At times, they make clouds brighter. At times, they warm the air. At times, rain pulls them down and removes them from the sky. At times, they are lifted high, remain longer, and cause the whole planet to receive less sunlight for a period of time. From the ground, people often see the sun rise and set, see day turn bright and then dark, see clear skies give way to clouds. These changes are so familiar that they can easily seem like the background of life. But behind that familiarity is a highly sensitive system. When clouds change, the amount of light reaching the ground changes. When ice becomes dark water, the way the surface absorbs sunlight changes. When a thin layer of tiny particles appears high in the atmosphere after a volcano, global sunlight can soften enough for scientific instruments to recognize. Earth does not need loud events every day in order to change. Sometimes, only a very thin haze in the atmosphere is enough to leave a trace. From far away, the blue planet still looks peaceful, but that peace is held by countless delicate balances. Clouds must come and go. Ice must reflect during the cold season and retreat during the warm season. The oceans must absorb and release heat. The atmosphere must hold enough warmth to keep water from freezing across the whole surface, but not so much that everything becomes severe. Light must be received, returned, softened, and divided along different paths. Among all those paths, tiny dust particles are not the largest actors, but they are one of the clearest signs that climate is sensitive, even to things almost impossible to see. A planet is not shaped only by oceans and continents. It is also shaped by the clouds that drift across it, the ice that brightens, the color of the ground, the clarity of the air, and the tiny particles suspended between the sun and the surface. When Earth is understood this way, light is no longer something that only falls from above. Light becomes a continuous flow of motion, received by the planet through millions of surfaces and billions of tiny particles. Some of it stays and becomes warmth. Some of it leaves and is lost to space. Some of it is redirected inside the thin atmosphere. And from that silent dividing, Earth's invisible shade begins to form. Within Earth's almost invisible shade, there is not just one kind of particle. The sky does not contain only dust in the familiar ground-level sense, not only dry particles lifted from roads, deserts, or ash. The atmosphere also holds extremely tiny liquid droplets, very light salt crystals, fragments of mineral matter raised by the wind, smoke particles born from fire, fine dark particles from combustion, and light-colored particles that form after certain gases transform in the air. They differ in size, color, composition, altitude, lifetime, and in the way they interact with light. From the ground, all of them may only make the sky look slightly hazy. But on the scale of the atmosphere, each type of particle is like a different kind of touch on the stream of light moving down toward Earth. Atmospheric scientists call these very small solid particles, or liquid droplets, drifting in the air aerosols. The word may sound dry, but the phenomenon itself is very close to the life of the planet. Every time ocean waves break apart, tiny droplets of salty water are thrown into the air. The water evaporates, and the salt remains as small particles that can drift with the wind. Whenever wind blows across dry land, mineral dust can leave the ground, rise upward, and travel across very long distances, sometimes crossing entire oceans before settling somewhere else. Every fire sends into the sky a mixture of fine smoke, small ash, gases, and dark particles. Every major volcanic eruption can carry material into the higher atmosphere, where some light-colored particles may survive longer than ordinary dust near the ground. Even cities, factories, ships, and vehicles leave behind tiny particles in the air that human eyes cannot separate one by one. Air, then, is never a completely empty space. Even on a day that seems clear, the atmosphere still contains countless tiny pieces of matter in motion. They may be few enough that the sky looks deeply blue and the horizon sharp. They may be numerous enough that the light becomes pale white, the sun near sunset turns redder, or distant mountain ranges fade into a blurred line that is hard to distinguish. People often sense this with their eyes, their skin, their breath, and the feeling that the sky is clear or hazy. Science looks at the same phenomenon through the scattering of light, the optical thickness of the atmosphere, the chemical composition of the particles, and their position within the layers of air. A tiny particle in the atmosphere does not remain still. It is lifted upward, pulled downward, blown sideways, swept into clouds, washed out by rain, or left to drift on if it is in a place where rain cannot easily reach. In the lower atmosphere, many particles have shorter lives because weather is always active. Rain can pull them down, wind can gather them together or thin them out. Warm air rising from the ground can lift them higher. But if particles appear in a higher layer, especially after a powerful enough eruption, they can remain longer and spread more widely because there are fewer familiar rainstorms there to wash the sky clean. Altitude itself changes the influence of a tiny particle. With the same composition, a particle near the ground and a particle in the stratosphere can have very different fates in the atmosphere. Size also makes a difference. Some particles are large enough to fall back down relatively quickly. Some are so small that they drift with air currents as if they almost have no weight at all. Particles that are extremely small can enter the microscopic processes of clouds. Larger particles can scatter light in different ways. Size does not only determine how long a particle can stay in the air, it also determines how it meets light. Sunlight contains many colors, many wavelengths, and many ways of interacting with matter. A tiny particle does not need to cover the whole sky in order to have an effect. Simply by lying along the path of light, it can cause that light to spread, change direction, be absorbed, or become part of the process that forms clouds. The color of a particle is one of the easiest signs to imagine. Light-colored particles often tend to return more sunlight. Sea salt particles, some sulfate particles, or particles with reflective surfaces can scatter light and allow less energy to travel straight down to the ground. Dark particles behave differently. Soot produced by incomplete combustion can absorb light more strongly, warming the layer of air around it. If those dark particles fall onto snow or ice, a bright surface that normally reflects well can become darker, absorb more heat, and lose part of its ability to send light back into space. Both may be called tiny particles in the atmosphere, but one can soften the light while the other can hold on to more energy. That difference makes the idea of cooling dust far too simple if spoken too quickly. Desert dust, sea salt, sulfate, wildfire smoke, soot, industrial pollution particles. Liquid droplets in fog, each has its own life. A layer of mineral dust crossing the ocean can make the sky hazier, but its mineral composition, its size, and its altitude will determine the true effect. A plume of smoke can both reflect some light and contain dark particles that absorb heat. A high-altitude sulfate layer after a volcanic eruption can reduce the amount of sunlight reaching the surface for a time, while the atmosphere is still carrying on countless other processes at the same time. No single label is enough to name every effect of suspended particles. In daylight, some particles make the sky appear whiter. They scatter light in many directions, so sunlight no longer feels as sharp as it does in very clear air. On days like this, shadows on the ground may become softer, the horizon more blurred, and the sun may sometimes look paler even though it is still there. At a mild level, this can seem ordinary, only a thin haze in the atmosphere. At a stronger level, it can make the entire landscape appear as if it has been placed behind a sheet of thin glass. But that sheet of glass is not glass at all. It is made of tiny drifting particles, suspended liquid droplets, and light being dispersed before it reaches human eyes. When the sun sinks low, the role of tiny particles becomes easier to see through color. Sunset light must travel through a much longer stretch of atmosphere than it does at midday. Along that longer path, light meets more gas molecules, more water vapor, more dust particles, and more tiny droplets. Shorter colors are scattered out of the line of sight more easily, leaving behind more yellow, orange, and red. If the upper atmosphere contains extra small particles after a major volcanic eruption, sunset colors can become deeper, last longer, and show violet or red streaks that seem more unusual than normal. The scene is beautiful, but that beauty begins with a very real meeting between light and matter. Beyond directly touching light, tiny particles also play a quieter role in forming clouds. Water vapor in the air does not always turn into liquid droplets easily on its own. It often needs very small points to cling to, such as a salt particle, a piece of dust, a smoke particle, or a suspended chemical particle. When water vapor gathers around those points, tiny water droplets begin to form. Many small droplets appear together, grow, drift in the air, and then become a cloud. A cloud seen from below may look soft and continuous, but inside are countless tiny droplets, each with its own history that began from an extremely small foothold. When the number of particles in the air changes, the characteristics of clouds can change as well. If there are many points for water vapor to cling to, the same amount of water can be divided into many smaller droplets. Under certain conditions, those smaller droplets can make a cloud brighter and better at reflecting sunlight. So suspended particles do not affect light only by standing directly in the path of the sun's rays. They also affect it indirectly by changing how clouds form and how clouds reflect. A particle too small to be seen on its own can become the starting point of a cloud droplet. Then that droplet becomes part of a white cloud, and that white cloud can send light back into space. But clouds are not simple mirrors, either. Low, thick, white clouds usually reflect a great deal of sunlight, making the surface beneath them gentler. High, thin clouds can allow much of the light to pass through, while also holding on to part of the heat escaping from the ground. Each kind of cloud lives at a different altitude, has droplets of different sizes, lasts for a different amount of time, and plays a different role in the climate system. When tiny particles influence clouds, they enter a network far more complex than the image of dust blocking sunlight. They can make clouds brighter, make cloud droplets smaller, change how long clouds survive, or in some cases contribute to effects that are harder to predict. The atmosphere does not respond with one single answer. Near the ground, Suspended particles also touch human life directly. A layer of fine smoke may make the light feel softer, but the breath heavier. A layer of pollution may make a city less glaring in the sunlight, while also taking away the clarity of the sky. A wind carrying desert dust can tint the air pale yellow, lay dust across cars, rooftops, and leaves, and eventually fall onto the sea or the land. A rainstorm after many hazy days can open the sky again, washing many particles out of the lower atmosphere and making the light sharper. These changes show that tiny particles are not only data in the atmosphere. They pass through the eyes, through the lungs, through clouds, through rain, through the color of sunset, and through the feeling of a clear or hazy day. In that atmospheric ocean, the origin of particles is never fully separate from the planet below. The sea sends salt into the sky. Deserts send dust. Burning forests send smoke. Volcanoes send gases and ash upward. Cities send particles born from combustion. Ships leave trails of particles along routes across the ocean. Wind receives them, mixes them, and carries them to unfamiliar places. A mineral dust particle can leave one continent and fall into another ocean. A sea salt particle can be born from a breaking wave and become the starting point of a cloud droplet. A particle from a wildfire can tint the sky in a place very far away. Tiny particles make Earth appear as an interconnected system, where land, sea, fire, wind, and light are constantly exchanging matter with one another. If we look closely at each type of particle, that diversity becomes even clearer. Sea salt particles are often brighter and more able to attract water, so they can take part strongly in forming cloud droplets. Mineral dust from deserts has a more complex composition and can reflect or absorb depending on its color and minerals. Sulfate particles are often light-colored and good at scattering light, especially when many of them appear high in the atmosphere after a major eruption. Soot, by contrast, is dark and absorbs light strongly, so it cannot be grouped with reflective particles as if all of them had the same effect. Wildfire smoke is a complex mixture, able to contain both lighter organic particles and black particles that absorb heat. In the atmosphere, a general name is only the beginning. The true properties of each particle determine how it affects light. The higher particles rise, where air currents move across wider distances and rain no longer washes everything clean in the familiar way. The more a thin layer of particles can become a global phenomenon. This is why major volcanic eruptions have a special influence. It is not because visible volcanic ash covers the sky for a long time, but because some of the gases lifted high upward can form small bright particles that survive longer in the stratosphere. When those particles spread around the planet, each one scatters only a very small portion of light. But their large number, great altitude, and broad area cause the effect to add up. Earth's surface can receive less sunlight for a time, enough for a trace to appear in measurements of temperature and light. Even so, every cooling effect from tiny particles must be understood within its limits. Many particles last for a shorter time than greenhouse gases. Many particles are unevenly distributed, concentrated more in some regions than in others. Their effects depend on clouds, rain, seasons, wind, altitude, and the color of the surface beneath them. A layer of particles may brighten clouds in one place, while somewhere else it combines with atmospheric conditions in a different way. One type of particle may reflect light well, but if it comes with harmful pollution, human health and ecosystems still pay a price. No simple idea is enough to turn a particle-filled sky into a healthy solution for the planet. Suspended particles in the atmosphere are therefore like a very small alphabet of the sky. Each type of particle is a character. Sea salt has one way of writing. Desert dust has another. Sulfate, soot, forest smoke, fine ash, liquid droplets each adds its own sign to the air. Sunlight passes through that alphabet and leaves its result in the color of the sky, in the brightness of clouds, in the amount of heat reaching the ground, in measurements from satellites, and in the very ordinary feeling people have when they look up at a clear or hazy day. The sky above is not as silent as it appears. It is constantly being rewritten by tiny particles. On the scale of a human life, many changes in this layer of particles come and go very quickly. A rainstorm can make the air cleaner within just a few hours. A wind can bring dust from far away in a single day. A large fire can change the color of the sky for many days. But on the scale of a planet, these fluctuations create a longer rhythm. The oceans continue sending salt upward. The deserts continue sending dust away. Volcanoes occasionally lift material into the high atmosphere. Human activity adds new particles to the atmosphere, with quantities and properties different from natural ones. Sunlight still descends every day, meeting an atmosphere that is never exactly the same as it was the day before. So when a ray of sunlight travels from space into Earth, it does not simply meet air. It meets a very thin layer of the world, filled with matter. It may meet a salt particle that once belonged to the ocean, a dust particle that once lay on a desert, a smoke particle once born from fire, a sulfate particle that began as volcanic gas, a dark particle that came from combustion, a tiny cloud droplet suspended in the sky. These encounters are too small for anyone to see individually, but when they happen across the entire atmosphere, they help determine how much Earth brightens, how much it softens, how much warmth it holds, and how much light it returns to space. In the thin layer of air surrounding the planet, tiny particles do not need to be seen in order to be present. They only need to drift there, between the sun and the surface, between the sea and the clouds, between fire and wind, between dry lands and rains that are beginning to form. Some scatter light, some hold heat, some help clouds come into being, some fall quickly, some travel very far. From those quiet differences, the sky is no longer a simple transparent space, but a living filter of the planet. And within that filter, the fate of light never depends only on the Sunday. It also depends on the tiny particles drifting silently through Earth's atmosphere. Over the wide oceans, there are mornings when low clouds spread out like a very thin white blanket. Seen from the sea surface, the cloud may seem only like a soft bright ceiling that dims the sunlight. Seen from outer space, those cloud bands look like soft mirrors drifting across the planet's surface, not reflecting with the cold brilliance of ice, not glittering like metal, but bright enough to return a large portion of sunlight toward the darkness beyond. When clouds cover the ocean, the dark water below receives less sunlight. When the clouds dissolve, the water surface opens again, absorbing more light and holding more warmth in the upper layer. A cloud may appear light, but its white shadow can change how an entire region of ocean meets the Sunday. Clouds are often seen as water vapor, and that is not wrong. But water vapor alone does not easily become tiny droplets suspended in the sky. In the air, water vapor needs very small points to cling to, points far smaller than a grain of sand, so small that the naked eye cannot separate them from the sky behind them. A salt particle from the sea, a piece of dust from dry land, a smoke particle, a light-colored sulfate particle, or another tiny particle in the atmosphere can become the place where water vapor begins to gather. When water vapor clings around that foothold, a very small water droplet forms. Many tiny droplets appear together, hang together in the air, reflect light together, and from far away merge into the familiar shape humans call a cloud. Inside a white cloud, there is no seamlessness like the human eye imagines. It is not a giant mass of cotton, nor is it pure water vapor standing still in the sky. It is a crowded world of countless tiny water droplets, small ice particles, moving air, water vapor, temperature, and microscopic particles that serve as starting points. Each cloud droplet is very small, but an entire cloud can stretch for tens, hundreds, or even thousands of kilometers. The softness of clouds is therefore a beautiful illusion. Behind that softness is a delicate physical structure, where tiny particles in the air help water vapor find a form. When the number of tiny particles in a region of sky changes, Clouds can change their properties as well. If there are fewer footholds for water vapor to cling to, the water inside a cloud may be concentrated into fewer droplets, making those droplets larger. If there are more footholds, the same amount of water can be divided among many smaller droplets. A greater number of small droplets creates a cloud whose surface reflects light differently. In many cases, a cloud made of many small droplets can be brighter, whiter, and able to return more sunlight to space. From the ground, that change may only make the light feel a little softer. From above, the brighter cloud becomes part of the great mirror Earth uses to reflect the sunday. This gives suspended particles in the atmosphere another indirect role. They do not only scatter light by themselves, they also change things much larger than they are. A salt particle cannot hide the sun, but it can help create a cloud droplet. A cloud droplet cannot cover an entire ocean, but trillions of cloud droplets can form a broad cloud layer. A broad cloud layer can cause the sea below to receive less sunlight for many hours. In this way, from a tiny crystal born at the crest of a wave, the light of an entire region of sky can be softened through many intermediate steps. The influence does not lie in one isolated particle, but in the chain connecting particle, water, vapor, cloud, and light. Over the ocean, this process unfolds in a very natural way. Waves break, white foam rises, and small water droplets fly into the air. The water can evaporate, leaving behind tiny salt particles. Wind carries those particles higher, mixing them into the moist layer of air above the sea surface. When conditions are right, water vapor clings to those salt particles and forms cloud droplets. From there, part of the ocean's salty breath becomes white cloud above the ocean itself. The sea does not simply lie beneath clouds. It also contributes a very small part to making them, as if the water surface were sending invisible seeds into the sky to soften the sunlight falling back upon it. In drier places, mineral dust can enter the sky by a different path. Wind sweeps across deserts, lifts very small grains of earth upward, and carries them far from where they were born. Some particles fall near their source. Others drift farther, crossing seas, cities, and forests before gradually settling somewhere else. During that journey, dust does more than blur the horizon. Some particles can interact with light, and some can take part in the formation of clouds or ice under certain conditions. Desert dust, then, does not belong only to the desert. Once it rises into the air, it becomes part of the atmosphere, part of the color of the sky, and part of the way light moves through the world. Smoke from fire carries a different character. Smoke can turn the sky gray, yellow, or red, depending on the thickness, composition, and position of the smoke layer. Inside smoke are many different kinds of particles. Some can scatter light and make the landscape appear more muted. Some darker particles can absorb light and warm the air. If smoke meets clouds, the interaction can become even more complex, because particles in smoke can affect the size of cloud droplets, the brightness of clouds, or the way clouds develop. A hazy sky after a wildfire can create a very vivid sunset, but that vividness is not separate from the heavy consequences of fire, smoke, and polluted air. Beautiful light does not turn the source of that light into something harmless. Clouds, therefore, are not simple mirrors that always cool. A low, thick white cloud usually reflects a great deal of sunlight, allowing the surface beneath it to receive less energy. But a high, thin, cold layer of cloud in the upper atmosphere can allow much of the light to pass down to the ground while also holding on to some of the heat escaping from below. The sky has many kinds of clouds, and each kind plays its own role. Some clouds are like bright veils that block sunlight. Some are like thin blankets that hold warmth. Some clouds both reflect daylight and influence nighttime heat. So saying that clouds cool or warm always needs to come with a question. At what altitude is the cloud? How thick or thin is it? How bright is it? Does it contain water droplets or ice crystals? What surface lies beneath it? And what time of day does it appear? This is what makes clouds one of the most difficult, but also one of the most beautiful parts of climate. Clouds change quickly. A region of sky may be clear in the morning, covered with clouds at noon, opened again after rain, then turn red as sunset arrives. Clouds are born from air that rises and cools. Clouds dissolve when the air becomes warmer or drier. Clouds move with the wind, grow when supplied with more water vapor, fall as rain when their droplets become heavy enough, or quietly vanish when conditions no longer support them. Within that soft changeability, tiny particles still hold the role of starting points. If the sky had no tiny particles at all, water vapor would have a harder time finding places to condense in the familiar way. In reality, the atmosphere always contains these footholds from both natural sources and human activity. A cloud above the ocean may carry the trace of sea salt. A cloud near dry land may be influenced by mineral dust. A cloud drifting through a region with heavy smoke or pollution may contain droplets that differ in number and size from those in a cloud formed in cleaner air. Every cloud, then, tells a story not only about water vapor and temperature, but also about the invisible particles that were present before the cloud took shape. Some traces of tiny particles on clouds are clear enough for satellites to see. Over the ocean, ship routes sometimes leave behind brighter cloud streaks, stretching like thin lines across a background of low cloud. Smoke and particles released from ships can increase the number of points where water vapor can cling, making cloud droplets in that region smaller and more numerous, and causing the cloud streak to reflect light more strongly than its surroundings. From the sea surface, people may not notice that shape. From above, the bright lines appear like thin brushstrokes drawn across the clouds. This is a very clear example of how tiny particles can change the shape and brightness of clouds, even though each individual particle remains beyond the direct sight of the human eye. Cloud streaks like these are not images meant to praise pollution. They are more like accidental experiments in the sky, showing that the atmosphere is sensitive enough for even a change in the number of tiny particles to make clouds different. A bright streak in the clouds can help science understand more about how suspended particles affect water droplets, light, and climate. But understanding that mechanism does not make the source of the particles harmless. Particles from combustion can still harm health and the environment. A brighter trace on a cloud still begins with materials that humans need to view with caution, not with simple fascination at a beautiful effect. On a natural scale, particles from the sea create a gentler, quieter rhythm. The ocean covers most of Earth's surface, and wind over the sea never truly stops. Every day, countless salt particles are lifted into the air. Some fall back quickly. Some enter the moist layer of air. Some become footholds for cloud droplets. Low clouds over the ocean reflect light very effectively, so small changes in their properties can affect how much sunlight the ocean receives. The sea, clouds, and salt particles therefore form a discrete loop of connection. The sea sends particles into the sky. The particles help clouds form. Clouds shade the sea from part of the sunlight, and the sea continues to evaporate beneath the remaining light. Over land, that relationship has more variations. Forests breathe out water vapor and many natural compounds that can take part in atmospheric chemistry. Dry soil sends dust upward when winds are strong. Volcanoes occasionally send gases and particles into very high layers. Cities and industrial regions add human-made particles with more complex compositions to the air. Each particle source has its own fingerprint. When those particles enter clouds, they do not only add numbers. They change how water vapor is divided into droplets, how light is reflected, and how rain may begin or be delayed under certain conditions. The sky above a forest, a great ocean, a desert, a volcanic region, or a city is never exactly the same. Those differences are not always visible to the eye. Two clouds may look nearly identical from the ground, while inside they contain different numbers of droplets, different droplet sizes, and different kinds of seed particles. A cloud may be slightly brighter in satellite data, while the person standing below only feels that the day is a little softer. A cloud region may last longer because smaller droplets have more difficulty merging into rain, but that effect still depends on humidity, air, movement, temperature, and many other factors. The atmosphere always resists explanations that are too neat. Each correct mechanism is only one part of a wider picture. Even so, one image still remains clear. Clouds are where the invisible becomes visible. Colorless water vapor gathers around unseen tiny particles, then becomes a white mass large enough to cover the Sunday. Small points suspended in the air become the centers of water droplets. Water droplets combine into cloud layers. Cloud layers change the path of light, and redirected light changes how much energy the surface below receives. From a salt particle smaller than dust on a fingertip to a bright cloud region stretching across an ocean, there is a very delicate but very real thread of connection. So when we look at a white cloud drifting slowly across the sky, we can see more than a soft shape. There is the ocean that has sent salt into the air. There is the wind that has lifted tiny particles and carried them far away. There is water vapor that has found a place to cling. There is temperature that has fallen just enough for droplets to take form. There is sunlight meeting a white surface, being scattered, being returned, being softened before it touches the ground. A cloud does not only block the Sunday. A cloud is the result of a long chain of conditions coming together where tiny matter and energy from the sun meet in the middle of the sky. The gentleness of clouds also makes it easy for people to forget their influence. A passing cloud can cool a yard for a few minutes. A low cloud layer over the ocean can change the amount of sunlight received by thousands of square kilometers of sea for many hours. Broad bands of cloud around the planet take part in the way Earth reflects light every day. If the properties of clouds change, even only in droplet size or brightness, the amount of light returning to space can change as well. Not every change is large. Not every change moves in the same direction. But the connection between tiny particles, clouds, and light is one of the reasons climate is both subtle and difficult to predict. In that picture, suspended particles are like very small workers building the softest part of the sky. They do not turn into clouds by themselves, but without them, many cloud droplets would have a harder time beginning. They do not cool the planet on their own, but by influencing the brightness and shape of clouds, they can help Earth reflect more or less light. They are not the only actors, because water vapor, temperature, wind, and altitude all matter. But they are a small link placed exactly where light, water, and air meet. When the sun rises high over an ocean covered with low clouds, white light falls downward and then bounces away from countless tiny water droplets. Each droplet reflects a very small portion. The whole cloud reflects more. The entire cloud region reflects still more. From outer space, that region brightens like a white patch on the blue sphere. Below, the sea receives less sunlight than it would under a clear sky. No loud sound accompanies this process. No hard boundary appears in the air. There is only light, water vapor, tiny particles, and the soft motions of the atmosphere together creating a mirror that never stands still. Somewhere else, a thin layer of high cloud spreading across the night sky can hold onto part of the heat escaping from the ground, making the night less cold. It is still cloud, but its role changes with altitude and time. By day, clouds can block some sunlight. By night, clouds can hold some warmth. Low clouds and high clouds are not the same. Thick clouds and thin clouds are not the same. Clouds over dark ocean and clouds over bright ice do not lead to the same result. This truth takes away overly easy answers, but it keeps the sky faithful to its own living nature, always changing, always dependent on context, always connecting small things with large things. Tiny particles in the atmosphere enter that living motion through many paths. Sometimes they make clouds whiter. Sometimes they make cloud droplets smaller. Sometimes they help delay rainfall because small droplets need time to collide and grow. Sometimes they are carried down to the ground by rain itself, ending their journey through the sky. Sometimes they remain in a dry layer of air only dimming the light without yet becoming clouds. Their role is not fixed, but in every role, they remind us that the sky is not merely an empty space between the ground and outer space. It is an environment filled with matter, filled with exchange, filled with small beginnings. When a person lies beneath the shade of a cloud and feels the sunlight soften, the feeling is very simple. The skin feels less hot. The eyes are less dazzled. The ground looks less bright. But above that, simple feeling is an entire structure of atmospheric complexity. Light has met countless water droplets. Those droplets once began around extremely tiny particles. Those particles once came from sea, land, fire, volcanoes, or human activity. Wind carried them to the right place. Temperature allowed water vapor to cling to them. A cloud formed, and in that very ordinary moment, part of the sun's light was returned to space. A cloud, then, can be seen as a place where Earth breathes out light. The planet receives sunlight from the sun, but does not keep all of it. Through clouds, Earth sends part of that light back into space. Through the tiny droplets inside clouds, the planet softens the stream of sunlight falling toward the surface. Through the suspended particles that help clouds form, the very small takes part in a very large rhythm of reflection. No giant dome is needed. No hard mirror has to surround the world. With only water vapor, tiny particles, wind, and light, the sky can create soft mirrors that drift across the planet every day. From far away, clouds make Earth a bright and living planet. Without clouds, the dark oceans would appear much wider. Without those white layers, many regions of sea and land would receive more direct sunlight. But clouds do not only beautify the image of Earth from space. Clouds are part of how the planet adjusts itself within light. When tiny particles change clouds, they touch one of the most important systems in climate. This is why the role of dust, salt, smoke, and sulfate does not end with making the sky hazier. They enter deep into the structure of clouds, where light is returned, water vapor is held high above, and climate is written by tiny droplets that never stop drifting. Between the sun and Earth's surface, clouds stand as a soft middle layer. They do not separate the planet from light, but give light more paths to follow. One path goes down to the sea. One path returns to space. One path is held in the warmth of the atmosphere. One path changes direction when it meets a water droplet. Tiny particles in the air do not control all of those paths, but they help begin many of them. From there, Earth's invisible shade is created not only by dust suspended in the sky, but also by the clouds born from those tiny particles, soft mirrors quietly reflecting the sun across the planet's sky. A very thin layer of particles high in the atmosphere leaves no clear boundary in the sky. No outline appears for human eyes to measure where that layer begins. No darkness falls onto the ground, like the shadow of a large cloud. After an eruption like Pinatubo, many people may notice that sunsets become deeper in color, that the setting sun looks softer, and that evening light lingers longer across distant cloud layers. But what the eye senses is only the first sign. To know what an almost invisible layer of particles is doing to the light of the entire planet, humans have to learn how to read the atmosphere through the very light that passes through it. Light is a silent messenger. Before it touches the ground, each ray has already passed through air, water vapor, clouds, dust, smoke, sea salt, tiny particles in the lower atmosphere, and sometimes even a very thin layer of sulfate in the stratosphere. When light leaves Earth and returns to space, it carries signs of the things it has encountered along the way. If the atmosphere is clearer, light passes through in one way. If the upper layers contain more tiny particles, light is scattered more, transparency decreases, colors change, and the amount of light reaching the surface becomes slightly lower. There is no need to see each particle. By seeing light change, scientists can recognize the presence of a particle layer suspended in the air. From the ground, the simplest measurements begin by looking up at the sun in a way more precise than ordinary eyes can. An instrument can measure the amount of sunlight passing through the atmosphere at different times of day. When the sun is high, light passes through a shorter layer of air. When the sun is near the horizon, light must travel through a much longer stretch of atmosphere. If there are many tiny particles in the air, the amount of light being weakened will change. By following that weakening, humans can estimate how clear or hazy the sky is, not by feeling, but through quiet numbers recorded hour by hour. That haziness is not like the thickness of a piece of cloth or the depth of a body of water. A sky may look almost normal, while the light passing through it has already been scattered more than before. Scientists often measure the degree to which the atmosphere weakens light, with a quantity that can be understood simply as optical haze or optical depth. If the optical depth is low, light passes through more easily. If the optical depth rises, more light has been scattered or absorbed along the way. After a major eruption, when sulfate particles become abundant in the stratosphere, that haziness can rise clearly. Humans do not need to stand inside the particle layer and see each particle. Light has left their signature on their behalf. On the ground, observation stations can only see the sky from certain locations. A station on an island, a station on a high mountain, a station in the middle of a continent, each one measures one part of the atmosphere above it. To see the entire planet, another point of view is needed. Satellites provide that view. From orbit, instruments observing Earth do not see the world the way human eyes admire a beautiful photograph. They measure light by color band, by direction of reflection, by level of energy. They look at clouds, oceans, ice, deserts, and the thin atmosphere surrounding the planet. When a layer of particles appears in the upper atmosphere, satellites can detect the change in the amount of light the atmosphere bends away. A satellite looking down at Earth can see the planet brighten or dim in very subtle ways. Where there are white clouds, light is strongly reflected. Where there is dark ocean, more light is held. Where the atmosphere contains many tiny particles, light may be scattered before it reaches the surface, or reflected back from within the air. The task of measuring instruments is not to see one individual dust particle, because the particles are too small and too numerous. They read the combined result of countless particles along the path of light. Like hearing rain on a roof without needing to count each drop, science can recognize a particle layer in the sky through the way light changes. After Pinatubo, the satellite view became especially valuable. Near the ground, many signs of the eruption had gradually settled. Ash fell, rain washed material away, winds blew, and the regions directly affected began living with the consequences. But in the stratosphere, a layer of tiny particles continued to spread. Instruments in orbit recorded that the upper atmosphere had become hazier to light. The amount of scattered light increased. The planet reflected back a slightly larger portion of the sun's energy. From those measurements, the almost invisible shade was no longer a guess. It became a signal that could be followed, changing over time, spreading with the winds, and then gradually fading as the particles disappeared from the upper atmosphere. There is a distinct beauty in the way satellites read Earth after an event like that. There is no explosion in the data. There is no dramatic image of an ash column after the eruption has passed. There are only measurement lines, color maps, and sequences of numbers showing that the stratosphere is holding more particles than before. A region of sky above the equator may change first. Winds carry the particles toward other latitudes. The particle layer spreads outward, grows thinner, and wraps around the planet like a faint mark with no edge. From one day to the next, satellites record that spreading through reflected light and weakened light. The sky becomes a vast record, and light is the ink written across it. Not only satellites, but laser beams from the ground can also help look into the layers of air above. When a laser beam is sent into the sky, part of the light is reflected back by gas molecules and tiny particles. By measuring the time it takes for the light to return and the strength of the signal received, Humans can estimate the altitudes where particles are concentrated. This method is like sending a call made of light into the sky, then listening for a very faint echo coming back down. If there are more particles in the upper layers, the light echo will be different. Through these small signals, the aerosol layer can be drawn by height, not only across the flat surface of a map. Weather balloons and research aircraft have also carried instruments into atmospheric layers, sampling air and measuring temperature, humidity, particle composition, size, and concentration. Each measurement is only a thin slice of the sky, but when it is combined with satellites, ground stations, and atmospheric models, the picture becomes clearer. A particle layer in the stratosphere is no longer an imagined veil. It has altitude, thickness, lifetime, chemical composition, particle size, and the ability to scatter light. These details help distinguish heavy ash that falls quickly from tiny sulfate particles that remain suspended for a long time, and distinguish a low-level smoke plume from a high-altitude aerosol layer that can affect global light. The data after Pinatubo also helped humans understand the difference between what the eye sees and what the climate feels. A person can stand under a blue sky and notice nothing unusual, but if the stratosphere above still contains many sulfate particles, the amount of light reaching the surface may already have decreased slightly. Air temperature at the ground does not respond instantly in a way that is easy to recognize from day to day because weather has too many fluctuations. Some days are still hot, some regions are still dry, some places still receive heavy rain, but when averaged over longer periods of time and wider areas of space, the softening signal can appear. Climate is not read through a single afternoon. Climate requires long measurement records, patience, and many layers of data compared together. The ocean makes that signal slower to read, but also deeper. Seawater absorbs and stores a great amount of heat. When incoming sunlight decreases slightly after a high-altitude particle layer forms, land surfaces may respond faster than the ocean, while the sea changes more slowly. Air, clouds, water, ice, and land all have their own rhythms. Scientists have to separate the influence of a volcano from natural variations such as changes in ocean currents, seasons, winds, and other climate fluctuations. Satellite data tells how light has changed. Temperature data tells how the surface has responded. Ocean data tells how energy entering the system has been stored or dispersed. No single instrument can tell the entire picture on its own. At times, it is the patience of measurement that makes a phenomenon more trustworthy. A vivid sky after a volcano can leave a strong impression, but the color of a sunset is only a visual sign. The data must answer quieter questions: at what altitude the particle layer sits, how quickly it spreads, how long it lasts, how much it weakens the light, how much energy it reflects back into space, and how it affects temperature. Those answers do not come from a single moment of looking up at the sky. They come from thousands of measurements, from many locations, over months and years, compared with the state of the atmosphere before the eruption occurred. Light helps humans connect those measurements together. The sun serves as a nearly steady source of illumination on the scale needed for daily observation. The atmosphere is the layer of matter that light must pass through. Satellites, ground stations, lasers, weather balloons, and research aircraft are different ways of reading the traces light leaves after interacting with that layer of matter. When the sky contains more particles, light changes the way it travels. When particles decrease, light passes through more easily. When clouds become brighter or darker, the amount of reflected light changes. When surface ice retreats, the planet holds more energy. All of these signals share one underlying language, where the sun's energy has gone. From outer space, measurements of light also show that Earth does not reflect evenly. Regions of thick cloud shine brightly. Ocean regions are darker. Ice-covered regions are brighter than open water. Deserts differ from forests. Cities differ from grasslands. A thin aerosol layer can drift above many different surface types, making the effect of the particles depend partly on what lies beneath them. Bright particles above a dark ocean may change the amount of reflected light more clearly than they would above an already bright cloud deck. Dark particles above snow and ice, or settling onto bright surfaces, can create a different effect. To understand a tiny particle, science has to place that particle in the right sky, at the right altitude, above the right surface, and at the right time of day. After major volcanic eruptions, climate models are also tested. Once scientists know that a layer of particles in the stratosphere is reducing the sunlight reaching the surface, they can place that information into a model and see how the model predicts Earth's response. Does temperature decrease by the observed amount? Does the ocean respond quickly or slowly? How does rainfall change? How does the stratosphere warm as the particles absorb part of the energy? A model does not replace the real sky, but it helps connect scattered observations into a system that can be tested. If a model can simulate the response after Pinatubo well, confidence in the way that model describes the climate's flow of energy increases a little. Measuring an almost invisible shade also requires distinguishing between incoming sunlight and heat emitted by Earth. During the day, the planet receives energy from the sun in the form of light. After the surface absorbs that energy, Earth emits heat back into space as infrared radiation. Clouds, water vapor, greenhouse gases, and other atmospheric layers can affect the outgoing flow of heat. High-altitude aerosols are mainly discussed for their ability to scatter incoming sunlight, but some particles can also absorb energy and change the temperature of the atmospheric layer where they exist. Climate is the balance between energy coming in and energy going out, so every measure, a particle layer after a volcano, can cool the surface while also warming the stratosphere slightly, because the particles absorb part of the radiation. Below, less light reaches the ground. Above, the particle layer is interacting directly with the energy flow. These opposite changes with altitude show that the atmosphere does not respond like a single uniform sheet of material. One layer may warm while the surface becomes cooler. One region may respond differently from another. One season may reveal the signal differently from the next. Reading the planet's shade is not only a matter of asking how much the average temperature drops, but also where energy has been redistributed within the air, land, and sea. On satellite maps, aerosol layers can be shown with artificial colors so the human eye can distinguish them more easily. Red, yellow, blue, and purple on a map are not the true colors of the sky, but the way science turns data into images. A darker or more intense region may mean more particles, greater haze, or stronger scattering of light. These maps make visible something that has no clear shape to human eyes. They allow people to see desert dust moving out over the Atlantic, wildfire smoke drifting across continents, volcanic particles spreading through the stratosphere, and sea salt or fog stretching across ocean regions. The atmosphere becomes a moving map of small matter. Although these images may look modern, the deeper principle beneath them is very simple. When light meets matter, light changes. If we know where the original light came from, and can measure the light after it passes through or reflects from the atmosphere, we can infer something about the matter in between. It is like looking at the color of water to guess whether it carries sediment, looking at the haze on glass to know dust has settled on it, or seeing evening light after a volcano and sensing that the sky has changed. Science expands that intuitive feeling with more precise instruments, wider fields of view, and longer periods of observation. Some measurements look up toward the Sunday. Some look sideways through the atmosphere at Earth's edge as the sun rises or sets behind the planet. Some look downward at the surface and read reflected light. Some send laser beams into the sky and wait for the signal to return. Each way of seeing has its own strength. Looking from the ground can monitor one location very carefully. Looking from a satellite can cover the globe. Looking sideways through the rim of the atmosphere can reveal particle layers by altitude. Lasers can show which layer above a measuring station contains the particles. When these perspectives overlap, the thin atmosphere begins to gain depth. That depth is very important because particles in the lower atmosphere and particles in the upper atmosphere do not have the same effects. A layer of dust near the ground can worsen air quality, reduce visibility, and affect health, but rain can wash it out more quickly. A layer of sulfate in the stratosphere may touch daily breathing less directly, but it can remain longer and interact with light over a much wider area. If we know only the total amount of particles in a column of air, but not where those particles are located, the picture is missing an important part. The atmosphere has height, not only a horizontal surface. The shade made by tiny particles has its own height as well, even if human eyes see the sky only as a blue dome. After Pinatubo, that height made the difference. Particles in the stratosphere were not pulled down quickly by rain the way many lower-level particles are. They had time to spread widely, to scatter light for many months, and to create a signal that lasted longer than ash clouds near the ground. Measurements by altitude showed that the aerosol layer was not simply a general haze. It had a specific position in the atmosphere. It thickened, spread outward, and then slowly thinned. As the particle layer descended or changed, the light signal decreased as well. By following height and time together, humans could see the life cycle of the volcanic shade. Those observations do not belong only to one past event. They help us understand later eruptions, major wildfire events, desert dust plumes, and the effects of human-made particles. When smoke from a large burning region rises high, satellites can follow the plume as it travels far away. When dust from the Sahara crosses the ocean, aerosol maps show a faint stream of matter drifting over the sea. When pollution in a region changes, atmospheric clarity and cloud properties can change with it. Each phenomenon has its own origin, its own composition, and its own altitude, but all of them are read through the same foundation: how the atmosphere has changed the light. There is a special humility in the way science looks at these tiny particles. No one can gather the entire atmosphere into their hands and examine every particle. No one can measure every point in the sky at the same time with a single instrument. All understanding comes from fitting together many signs: how much sunlight has weakened, how the sky has become hazier, where satellites see the particle layer, what ground stations record, how temperature responds, and whether models can reproduce the changes. To understand the atmosphere is to accept looking through traces, then patiently assemble them into a picture close enough to the truth. That patience also keeps humans from reaching conclusions too quickly. A slightly hazy sky does not automatically reveal which kind of particle is there. A cooler day does not automatically come from aerosols. A red sunset is not always a sign of a volcano. Sky color can be affected by water vapor, dust, smoke, clouds, the angle of the sun, and many other factors. Data must be compared, tested, and placed in context. Here, the appeal of science does not lie in giving a rushed answer, but in the ability to see many possibilities at once and gradually remove the ones that do not fit. When the measurements point in the same direction, the almost invisible shade becomes clearer. After a major eruption, stratospheric haze increases. Satellites record more light being scattered. Average surface temperature softens for a period of time. Sunsets, in many places, change color. Climate models reproduce part of the response when the aerosol layer is included in their calculations. No single sign has to carry the entire conclusion. It is the convergence of many signs that gives the phenomenon its weight. The sky grows dimmer and the data becomes brighter. From that perspective, satellites are not merely machines flying around the planet. They are like very patient observers, reading each day the light reflected from clouds, oceans, ice, land, and atmosphere. They pass through regions of brightness and darkness, recording changes by season, by storm, by volcano, by dust, by smoke, by melting ice and cloud cover. Each orbit adds a new slice. Each year of observation adds another layer of time. Thanks to these quiet observers, Earth is no longer understood only through what humans feel while standing on the ground. The planet is seen as a system of light that is breathing, reflecting, holding heat, and changing. When night falls over one half of Earth, satellites continue measuring other forms of energy. When day arrives on the other half, sunlight again provides a new record of clouds and aerosols. The alternation of day and night helps scientists separate many processes. Incoming light, outgoing heat, clouds reflecting by day, clouds holding warmth by night, tiny particles scattering sunlight, greenhouse gases trapping infrared radiation. The planet turns beneath the instruments, and each rotation reveals another part of the energy balance. The shade made by tiny particles is only one stream of signal among many, but it is subtle enough to remind us that climate cannot be read by the naked eye alone. The stratosphere after Pinatubo gradually became clear again, but the measurements remained. They became the scientific memory of a period when Earth received less light because of a high-altitude particle layer. That memory is not as loud as the memory of an eruption, but it lasts longer in human understanding. It helps explain why some volcanoes can bring temporary cooling. It helps test how climate responds to changes in incoming sunlight. It helps distinguish the short-term effect of aerosols from the long-term accumulation of greenhouse gases. It also helps reveal the limits of any idea that simplifies the sky into a curtain that can simply be pulled down or lifted up. An almost invisible layer of shade only becomes visible when humans learn to look through many different eyes. The eyes of a person standing beneath a sunset see deep red. The eyes of a ground instrument measure weakening sunlight. The eyes of a satellite see particles spreading around the planet. The eyes of a laser find the height of the hazy layer. The eyes of a model try to connect all of these things into one shared flow of energy. Each set of eyes has limits, but when placed together, they reveal an Earth far more delicate than its peaceful blue and white appearance in photographs from space. Within that thin atmosphere, no phenomenon is completely isolated. A tiny particle changes the direction of light. A layer of particles makes a region of sky hazier. A hazier region of sky causes the surface to receive less energy. The ocean responds slowly. Clouds respond in their own way. Average temperature shifts slightly, then blends into many other variations. Data must follow each step, from light to particles, from particles to energy, from energy to climate. That is how an almost invisible phenomenon is brought out of the haze of perception and becomes knowledge that can be tested. When we look up at the sky on an ordinary day, it is models calculating the flow of energy through atmospheric layers. All of them follow a question hidden deep inside everyday sunlight. Before sunshine touches Earth, what has the atmosphere done to it? The answer never has only one line. Clouds return part of it. Ice returns part of it. The ocean holds more. Bright particles scatter. Dark particles absorb. The stratosphere after a volcano dims the light. Greenhouse gases hold onto heat emitted from the surface. Rain washes many particles out of the lower layers. Wind carries particles far away. The ocean holds the memory of heat longer than air does. Light passes through this entire air network and leaves traces in the data. Thanks to those traces, the planet's shade is no longer a vague image. It becomes a measurable part of how Earth receives and returns energy. From far away, the blue planet still shines in sunlight. White clouds still curl around the oceans. Ice still reflects at the poles. Deserts remain pale yellow beneath the sunday. The sea remains dark and deep. But between all those surfaces and the sun, there is a layer of air being read every day through light. In that layer of air, tiny particles can come from sea, land, fire, volcanoes, or humans. They can vanish quickly in rain, or remain for a long time in the upper atmosphere. They can make the sky hazier, clouds brighter, sunsets redder, and the surface gentler. And when humans learn to measure those very small changes, a layer of shade, almost impossible to see, begins to take shape in our knowledge. Not the shape of a cloud, but the shape of light after it has passed through Earth's atmosphere. There are mornings in the city when sunlight does not fall onto the street with its familiar clarity. The sun is still there, above the rooftops, the tall buildings, the power lines, and the streams of vehicles moving past one another. But the light seems paler, as if filtered through a sheet of frosted glass suspended in the air. Buildings at the end of the street lose some of their edges. The sky is not exactly cloudy, and not truly blue. Everything seems to sink into a very light, gray-white, enough for the eye to notice, but not enough to call darkness. The sunlight becomes softer, but breathing does not become easier. The horizon softens, but the air is not clearer. A layer that screens light in this way can make the day less glaring, but that softness is not the sign of a healthy sky. Inside the haze of a city are countless tiny particles born from human activity. When fuel is burned in engines, factories, ships, incinerators, or other industrial processes, the air receives very small particles along with many different gases. Some light-colored particles can scatter sunlight, keeping part of it from traveling straight down to the ground. Some dark particles absorb light, warming the layer of air through which they drift. Some particles remain in the atmosphere for only a few days. Some are pulled down by rain after a spell of humid weather. Some travel far from where they were released, mix into other regions of sky, and then settle onto land, into the sea, onto leaves, rooftops, snow, or ice. Weakened sunlight does not always mean something pleasant. A less glaring afternoon beneath a layer of polluted haze is different from a gentle afternoon beneath clean white clouds. In both cases, human eyes may receive less direct light. But clouds are a natural part of the water cycle. While many pollution particles come with substances that can harm the body and the environment, a natural mist over a meadow in the early morning fades when the sun rises higher. Fine particles in a city can slip into the lungs, move through the bloodstream, settle on leaf surfaces, reduce visibility, change the color of the sky, and force daily life to adapt to heavier air. Both can soften light, but their origins and costs are not the same. There is a paradox that can easily be misunderstood. Some human-made particles are able to reflect light, helping to mask a portion of the warming caused by greenhouse gases. That does not turn pollution into something beneficial. It only shows that climate is complex enough for a harmful factor in daily life to create a narrow cooling effect in the flow of incoming light. That cooling is not clean, not even, not lasting, and it does not solve the deeper cause. It is like a smear on a window making sunlight less harsh, while the room remains full of dust and the people inside still have to breathe poorer air. Greenhouse gases and suspended particles do not live in the atmosphere in the same way. Carbon dioxide can remain for a very long time and accumulate over time, like a thermal blanket growing thicker within the climate system. Many tiny particles in the air have much shorter lifetimes. They can be washed down by rain, diluted by wind, chemically transformed, or fall out of the atmosphere. This difference in lifetime means the two kinds of effects cannot simply cancel each other out. One is the long-term accumulation of trapped heat. The other is a short-term, unevenly distributed screen of light, changing with wind, rain, seasons, emission sources, and particle composition. If there are many light-colored particles in the atmosphere, part of the sun's light can be scattered back into space. The surface below receives less energy. In some industrial regions in the past, the sky became hazier, less sunlight reached the ground, and measurements recorded a reduction of sunlight at the surface. But along with that screening of light came smoke, fine particles, acid rain, damaged health, affected crops, and cities that lost their clear skies. As air standards improved, many places became brighter, clearer, and easier to breathe in. Stronger sunlight can reveal part of the warming that had been masked by reflective particles, but a cleaner sky is still necessary for the life beneath it. A polluted sky does not make the planet healthy simply because it can reflect a little more light. A layer of sulfate particles from industrial activity can scatter sunlight, but sulfur compounds are also connected with acid rain and environmental problems. Soot can absorb light, warm the air, and then, when it falls onto snow or ice, darken the surface and reduce its ability to reflect. Fine particulate matter can travel deep into the respiratory system. Nitrates, organic compounds, sulfates, black carbon, and many other mixtures do not behave in the same way. In the real atmosphere, they do not appear separately like categories in a neat table, but often mix together into a complex layer of matter that touches both light and health. A city submerged in haze does not only receive less direct sunlight. That city also breathes within the very layer of particles that is blurring the sky. Windows gather dust more quickly. Leaves lose their clean green appearance after many dry days. People sensitive to poor air feel dry throats, stinging eyes, and heaviness in the chest. Car lights and street lights develop wider halos in the evening. Sunrise and sunset may become redder, more beautiful in a visual sense, but that beauty is not separate from the matter suspended in the air. The red of evening light passing through fine dust is not the same as the red of a healthy sky after rain. Both can make the eye pause, but only one brings the feeling of breathing more easily. On a regional scale, pollution particles can also change clouds. When the air contains more tiny points for water vapor to cling to, clouds may contain more small droplets. Under some conditions, clouds become brighter and reflect more light. Under other conditions, changes in droplet size can influence how rain forms, causing clouds to last differently. Tiny particles enter the life cycle of clouds, not merely standing outside them as a layer of dust that blocks sunlight. An exhaust plume from ships can leave traces in low clouds over the ocean. An industrial region can make cloud droplets different from those in cleaner air. These effects help science understand the atmosphere, but they do not make the pollution source harmless. Some traces of humans in the sky are very delicate. A ship route across the ocean can leave a brighter cloud streak in satellite images. A large city can create a region of air with more particles than the surrounding countryside. An industrial area can make the sky look milky white on stable weather days. A severe wildfire season can carry smoke across many regions, making the sun look like a pale red disk in the afternoon. These traces do not always have a clear shape to human eyes, but light still passes through them, is redirected by them, is held by them, is dimmed by them, and then carries those signs into the data from observation stations and satellites. Human-made particles are also not distributed fairly across the planet. They concentrate more heavily near emission sources, near industrial regions, cities, shipping routes, fires, or areas that use dirty fuels. Wind can carry them far away, but it does not make every place the same. One region may endure hazy air, while another remains clear. One community may breathe far higher levels of fine particles than another. The light screening effect of pollution particles, when it exists, is not spread evenly like a delicate and fair curtain around Earth. It is patchy, fast-changing, tied to specific emission sources, and bound to very real inequalities in daily life. Even their climate effects are more regional than those of greenhouse gases. After carbon dioxide becomes well mixed in the atmosphere, it has a long-lasting global influence. Many aerosol particles concentrate near their sources and survive for shorter periods of time. A particle layer in the northern hemisphere can have a different effect from one in the southern hemisphere. Particles over a dark ocean can change reflectivity more clearly than particles above an already bright cloud layer. Particles in the lower atmosphere can be pulled down by rain, while particles that reach higher layers can remain longer. Each of these details removes any simple statement, such as dust cools the planet. A more accurate sentence must always move more slowly. Some particles, under some conditions, in some locations, can reflect light and create a cooling effect, while still causing many harmful consequences. The difference between screening light and healing the climate is the key point. Screening light speaks only about one part of the incoming sunlight. Healing the climate must touch the whole system. The cause of greenhouse gas accumulation, the energy being trapped, the oceans absorbing heat, the ice changing, ecosystems under pressure, and the air humans breathe. A reflective particle layer may soften temperature in a narrow sense, but it does not make greenhouse gases disappear. It does not reverse ocean acidification caused by carbon dioxide dissolving into seawater. It does not restore lost forests, protect human lungs from fine particles, or resolve unstable rainfall and other complex impacts. Weakening light is not the same as bringing the system back into balance. We might imagine a garden beneath a dirty mesh screen. The sunlight passing through the screen may feel less harsh. The leaves below may receive less direct light for a few hours, but if that screen releases toxic dust, makes the air harder to breathe, dirties the soil and water, and harms insects and the people tending the garden, then that shade is not protection. A polluted atmosphere carries the same kind of paradox. It may make sunlight less glaring in some places, but the cost does not lie in the light alone. The cost lies in lungs, in rain, in soil, in water, in surfaces coated with particles, and in the distortion of a system that needs clean air in order to sustain life. Many pollution particles can be washed out of the lower atmosphere after rain. After days of heavy air, rain falls and opens the sky, sharpens the horizon, brightens the leaves, and makes roads reflect light more cleanly. That feeling shows how quickly near-surface particle layers can change. A rainstorm can bring a few hours or a few days of cleaner air. But greenhouse gases do not disappear like dust after rain. This difference makes reliance on reflective particles unstable. If particle sources decrease, the short-term screen of light decreases with them. If greenhouse gases continue to accumulate, the trapped warmth remains. A cleaner sky is something to welcome, but that cleanliness also makes the larger task clearer, reducing the long-term causes of heat retention rather than relying on a harmful haze. In industrial history, humans once unintentionally created significant changes in the clarity of the atmosphere. Regions that burned large amounts of coal, heavy oil, or dirty fuels could create grayer skies, more acid rain, and dirtier surfaces. When air cleaning technologies improved, environmental rules became stricter, and fuels became cleaner, many places saw clearer skies. That greater clarity helped sunlight reach the surface more strongly, bringing clear benefits for health and the environment. At the same time, science recognized that part of the previous cooling effect from aerosols had masked a portion of the warming caused by greenhouse gases. Recognizing that does not make pollution worth preserving. It only makes the climate problem more honest. That honesty requires a distinction between two feelings: comfort under softened sunlight and safety in healthy air. On a day when white clouds soften the sun, people may move more slowly beneath the sky. On a day when pollution weakens the sunlight, the body has to filter tiny particles that do not belong in the lungs. A sulfate aerosol layer in the stratosphere after a volcano can create a temporary cooling effect, but the event that produced it is still a powerful, uncontrolled eruption with local consequences. A layer of pollution, particles from human activity, can reflect part of the light, but its source is tied to illness, environmental decline, and other atmospheric problems. Softer sunlight is only one detail in a much larger picture. Clean air does not mean an empty atmosphere. A healthy atmosphere still contains clouds, water vapor, sea salt, natural dust, biological particles, ordinary chemical processes, and Earth cycles of moving matter. Cleanliness here does not mean removing every particle from the sky, because the natural atmosphere always contains particles. Cleanliness means reducing harmful particles, reducing mixtures from combustion and pollution, and reducing substances that damage people and ecosystems. Earth does not need a completely particle-free sky in order to live. Earth needs a sky where natural processes are not weighed down by harmful material that humans add too quickly. In the lower atmosphere, the presence of fine particles can be felt in every breath. In the upper atmosphere, a reflective particle layer can be recognized through light. These two layers differ in their distance from daily life, but they are not completely separate in the way we think about climate. An idea that may sound appealing on paper, adding reflective particles to cool the planet, becomes more complicated as soon as it is placed inside the real atmosphere. Where will the particles be? How long will they last? How will they affect clouds? What will they do to rainfall? Which regions will cool, and which regions will face harmful changes? What might chemical reactions in the upper atmosphere do to ozone? Who benefits, and who carries the risk? An artificial shade is never only a matter of light. We do not need to go deeply into technical details to see that complexity. The atmosphere connects all regions through wind, heat, water, vapor, and motion. A change in light can touch clouds. A change in clouds can touch rain. A change in rain can touch crops, rivers, forests, and water supplies. A high-altitude particle layer may reduce average temperature. But average temperature does not tell us that every region will respond in the same way. The planet is not a room with lights that are too bright, where all we need is one extra filter. The planet is ocean, land, ice, wind, rain, living things, and human beings, all sharing one thin atmosphere, but not sharing risk in the same way. In everyday life, people often want a neat answer. If the world is warming, find something that cools it. If the sunlight is too strong, find a way to shade it. But climate does not behave like a single object. Some reflective particles can cool temporarily, while other particles warm. Particles can affect clouds. Particles can harm health. Particles can last for a shorter time than greenhouse gases. Particles can be distributed unevenly. Particles can fall onto land, onto ice, or into the ocean. One small phenomenon opens into many different consequences. Every view that moves too quickly misses the most important part. The climate system always answers through many paths at once. A clear sky after rain often brings a feeling of lightness. Streets look sharper, trees look fresher. Buildings at the end of the road come into clearer focus. The sunlight may be stronger, but the air feels better to breathe. That feeling helps distinguish between the softness of light and the cleanliness of the sky. Humans do not need a layer of polluted haze to live more comfortably. The body needs air with fewer toxic particles. Forests need rain and healthier soil. The ocean needs a more stable climate system. A clean sky may allow more sunlight through, but that clarity is the foundation of a healthier planet. While the excess energy must be addressed at the long-term cause of heat retention, human-made suspended particles point to a paradox of the industrial age. While greenhouse gases cause the planet to hold more heat, some pollution particles reflect away part of the light and mask a portion of the warming. These two opposing effects exist at the same time, which means the temperature we observe is not the trace of one factor alone. When particle pollution declines, the sky becomes cleaner and health is better protected, but the light screening layer also becomes thinner. If greenhouse gases have not fallen enough, the warming that had been hidden can become more visible. That is not a reason to keep pollution. It is a reason to look directly at the long-term sources of retained heat, instead of mistaking harmful haze for a shield. In a system as thin as the atmosphere, everything added to it has its own life. A sea salt particle can become a cloud seed and then fall back down in rain. A sulfate particle from pollution can scatter light, but also take part in harmful reactions. A soot particle can absorb sunlight and then darken snow when it settles. A smoke particle can pass through many regions before disappearing. Each tiny particle carries its origin with it. When light meets them, light only sees their size, color, composition, and position. But humans must also see their sources, their health consequences, their environmental effects, and the fairness between regions forced to live beneath that hazy air. The fascination of aerosols lies in the way very small things can have very large effects. The danger of oversimplified thinking lies there as well. If we look only at reflection, A layer of light-colored particles can seem like a thin curtain helping the planet cool. If we look more fully, that curtain may be woven from pollution, illness, changed rainfall, complex atmospheric chemistry, and risks that are not shared equally everywhere. Climate has to be understood through the whole picture, not only through the portion of light returned to space. A planet does not become healthy simply because its surface receives less sunlight for a time. Where the sky becomes clear again, people can see mountains more sharply, deeper blues, and white clouds with crisper edges. That clarity does not deny that sunlight can be strong. It only shows that the air contains fewer harmful particles. It also highlights the difference between natural clouds and pollution, between the healthy shade of a cloud and the heavy haze of fine particles, between the water cycle and the trace of burned fuel. Earth already has its own ways of reflecting light. Clouds, ice, snow, oceans, deserts, and natural particles in the air. Humans do not need to add a layer of pollution to do work that nature already performs through far more delicate mechanisms. What remains in that unwelcome screen of light is a lesson in distinction. Cooling in the physical sense does not always mean good. Reflecting light does not always mean protection. A hazy sky does not always mean a gentle sky. An effect can be true in one small part of the system, while still being wrong for health, wrong for ecosystems, and wrong for sustainability. Pollution particles help humans see the complexity of climate more clearly, but they do not deserve to be treated as allies. They are a reminder that a planet can receive less sunlight and still not be healed. When sunlight passes through a cleaner atmosphere, more rays reach the ground. The surface receives energy more clearly. Trees, rooftops, water surfaces, and streets become brighter. The air is easier to breathe. The horizon opens. That brightness may raise harder climate questions, because the masking effect of pollution is no longer the same as before. But the sky should not have to be dirty in order to hide excess heat. A healthier world is not a world that keeps a harmful haze. It is a world that reduces what makes the atmosphere hold heat for too long, while also giving people back clearer air to breathe. Within the thin atmosphere around Earth, tiny human-made particles have become part of the signature of this age. They are present in the color of many city skies, in the smoke trails of ships, in the fine dust that lingers after rainless days, and in satellite maps that record the haziness of the air. They change the path of light, but they also change life. They can block part of the sunlight, but they cannot hide the fact that climate needs to be stabilized through deeper, cleaner, more lasting causes. A haze in the sky is not an answer for the planet. It is only a sign that light, matter, and human beings are bound together in a system far more sensitive than everyday perception suggests. When thinking about tiny dust particles that can cool an entire planet, the hardest part is not believing that they have an influence. The hard part is not mistaking that influence for something good. Volcanoes can create a temporary layer of reflective particles, but eruptions are not something humans wish for. Pollution can weaken sunlight in some places, but dirty air is not a climate gift. A shade is truly valuable only when it does not poison the person standing beneath it. The sky needs to be seen in the same way, not only by asking whether the light has softened, but by asking what is making the light soften, how long it remains, whom it touches, where it causes harm, and whether it addresses the real cause or merely hides the symptom. Above every city, every forest, every ocean, and every ice-covered region, the atmosphere continues to filter light in very small ways. Some filters are natural, coming from clouds, water vapor, sea salt, and mineral dust. Some are born from volcanoes, lasting for a while before disappearing. Some are added by humans through smoke, fuel, and industry. Not every filter is the same. Not every shade is protection. Between sunlight and Earth's surface, tiny particles can make the sun feel gentler, but only a healthy atmosphere can keep that gentleness from being paid for with breath, rain, soil, water, and the life below. When a layer of very small particles can soften sunlight, an almost unavoidable thought begins to appear. If volcanoes once made Earth cooler for a time, could humans create a similar reflective layer? The idea seems simple when it exists only as a sentence. The planet is warming. More energy is entering than escaping as heat, so perhaps we only need to return part of the light before it reaches the ground. A shade thinner than cloud, higher than weather, broader than continents. An artificial reflective layer, standing between the sun and the surface, making sunlight less harsh over a warming world. The idea is appealing because it borrows its image from nature. Pinatubo carried particles into the upper atmosphere. Those particles scattered light. Earth's surface cooled temporarily. Satellites measured the trace. Thermometers recorded the response. A real chain of events can make the idea of creating shade sound as if it is following a path nature has already opened. But nature is not a simple blueprint for humans to copy. A volcanic eruption is a violent, uncontrolled event that causes great harm where it occurs, and only afterward leaves behind a temporary particle layer high above. Taking one part of a volcano's effect out of that entire context can easily create the feeling that the atmosphere is only a pane of glass that can be dimmed when needed. The atmosphere is not like glass. It moves, swirls, mixes, lifts water vapor, carries dust far away, creates clouds, creates rain, holds heat, loses heat, and changes by season and by region. A reflective particle layer introduced into the upper atmosphere would not only meet light, it would also meet atmospheric chemistry, high-altitude winds, the processes of cloud formation below, the distribution of rainfall, the differences between ocean and continent, between the tropics and the poles, between places where many people live and places where almost no one does. A change designed to affect average temperature can touch many things that do not appear inside that average number. Global average temperature is a necessary way of seeing, but no one lives inside global average temperature. People live within the rainy season of a delta, the dry season of a plateau, a rice crop, a water source, a river, a prolonged heat wave, a storm season, a snowmelt season, a fire-prone forest. If a reflective layer makes the planet cooler on paper, the question does not end there. Which regions cool more? Which regions cool less? Where does rainfall change? Are monsoons shifted? How does ice respond? How does the ocean absorb heat? A small change in light can move through the climate system like a ripple across water, touching different shores in different ways. The temptation of artificial shade lies in the feeling that light can be separated from everything else. Just reduce sunlight a little. Just return part of the sun's energy. Just soften temperature, while the world finds ways to reduce greenhouse gases. But light does not enter Earth alone and then disappear. Light warms the ocean's surface, causes water to evaporate, helps create clouds, and influences pressure, wind, and rain. Light warms land differently than sea. Light falling on ice is different from light falling on forests. Weakening light high above may cool the surface, but it can also cause convection, water vapor, and rainfall to respond in ways far more complex than a patch of shade in a yard. An umbrella over the head can make a person on the street feel cooler, but an umbrella for the whole planet would not shade only one person, one street, or one summer. It would shade oceans, forests, ice, cities, fields, mountains, deserts, dry regions, and rainy regions all at once. One place may wish for less heat. Another may need sunlight for the growing season. One region may need stable rainfall. Another may already receive too much rain. No shade can cover Earth without touching the differences among the places living beneath it. The wider we look, the more the original idea loses its simplicity. Alongside rain and wind, the ozone layer also belongs within the region of concern. The ozone layer is part of the atmosphere that absorbs much of the harmful ultraviolet radiation before that radiation reaches the surface. Particles in the stratosphere do not only reflect light. Their surfaces can also become places where chemical reactions occur. If upper atmosphere chemistry changes, the ozone layer can be affected. This is not an image easily seen by the eye. No dramatic color immediately warns people at the ground that a reaction is taking place high above. But the atmosphere is full of quiet processes like this, where a change created for the sake of light can bring a change in the chemistry of the air layer that protects life. There is another risk that comes from time. Greenhouse gases last a long time. Some reflective particles last much less time. If a civilization depends on a particle layer to mask part of the warming, that layer has to be maintained continuously. If war, crisis, error, lack of agreement, lack of resources, or an unforeseen event causes that screen to stop quickly, the hidden warming could appear over a much shorter period than humans and ecosystems are able to adapt to. Dependence on an artificial shade is not the same as fixing the cause of heat retention. It is like holding a heavy door by hand. When the hand grows tired or lets go, the weight is still there. There is a deep difference between reducing a cause and covering a symptom. Greenhouse gases hold on to heat escaping from the surface. If the amount of those gases can be reduced, Earth's energy system is gradually brought back toward a less forced state. A reflective particle layer, by contrast, mainly affects the incoming light. It can make the surface temperature gentler for a time, but it does not make carbon dioxide disappear on its own. It does not stop the ocean from absorbing carbon. It does not address the full chemical change taking place in the sea. It does not restore ecosystems that have been broken. It does not erase the source of the imbalance. It only places an opposing effect on one part of the energy flow. If a house is hot because there is a slow source of heat inside the walls, adding curtains may keep some sunlight out, but the heat source inside the walls continues. The house may feel more comfortable for a while, but it will still need another kind of repair. Earth is countless times more complex than a house. The ocean stores heat for decades. Melting ice makes the surface darker. Forests, soil, clouds, water vapor, and ocean currents all respond in their own rhythms. A reflective layer high in the atmosphere can change the amount of incoming light, but it cannot replace the harder work as a whole, reducing heat, trapping gases, protecting ecosystems, cleaning up energy, preserving forests, protecting water, and adapting to changes that have already happened. The temptation of a quick solution is often strongest when the problem is too large. Planetary warming is a large problem. It stretches across generations, countries, economic systems, patterns of consumption, political decisions, and overlapping interests. An idea that seems to act quickly on temperature can easily pull the imagination toward it. But speed is not always a friend to a complex system. Doing something quickly before it is fully understood can create rapid reactions in places where they are not wanted. The atmosphere has no simple undo button. The ocean does not forget heat as soon as humans change their minds. Rain and wind do not sign an agreement promising to respond exactly as an average chart suggests. The more artificial shade is placed into real life, the clearer the questions of fairness become. Who has the right to decide that the shared sky should be dimmed? Which country gets to say yes? Which country must suffer if rainfall changes in a harmful way? How would farmers in a dry region be asked if their rainy season shifted? What would a small island think if temperature softened, but rain and storms changed in another way? A wealthy city may be better protected from risk, while poorer communities may have to live with unwanted effects. The atmosphere has no borders like a political map, but decisions about the atmosphere still fall onto very specific human beings. Volcanoes do not ask permission before erupting. Nature does not hold a vote about a sulfate layer in the stratosphere. Humans are different. A deliberate action toward the global atmosphere would carry an ethical responsibility that a natural event does not. We cannot only ask whether it can cool the planet. We must also ask who controls it, who monitors it, who is responsible, who has the right to stop it, who is compensated if harm occurs, and who ensures that a temporary measure does not become an excuse to delay harder but more necessary changes. The sky is shared, but the power to change the sky is never evenly distributed. In simulations, a reflective layer can reduce average temperature. In daily life, climate is not experienced as an average line. An unstable rainy season may matter more than a cooler number. An ice-covered region responds differently from a tropical forest. A country that depends on monsoons will care about rainfall as much as temperature. A coastal region that depends on coral reef ecosystems will care about heat, ocean acidity, and the light reaching into the sea. A layer of particles high in the atmosphere may not directly touch every one of these problems, but it does not fully solve them either. It softens one part of the system while many other parts remain under pressure. There is a quieter danger as well, the feeling of being allowed to slow down. If an artificial shade makes surface temperature gentler, humans may more easily forget that greenhouse gases are still accumulating. Industries dependent on fossil fuels may treat it as a reason to delay. Difficult decisions about energy, land, transportation, industry, and consumption may be pushed into the future. In that case, a temporary measure affects not only the atmosphere, but also social will. It may soften Earth's surface while slowing the urgency needed to address the cause. A layer of shade in the sky can become a layer of shade in thought. Science can study an idea without endorsing its use. That distinction is essential. Research helps us understand atmospheric responses, risks, the limits of models, and what might happen if a country, a powerful group, or some event pushes the world toward intervention. Not studying also carries risks, because lack of understanding does not make the idea disappear. But research does not mean a green light. Knowing that a mechanism exists does not mean knowing how to use that mechanism safely. Earth has shown that aerosols can reflect light. Earth has not shown that humans can turn that fact into a fair, sustainable, harmless tool. One of the largest limits lies in the models. Climate models are a major achievement of modern science, but a model is still a simulation of an extremely complex system. Clouds remain difficult. Rain remains difficult. Regional responses remain difficult. Small changes in how a model handles particles, clouds, oceans, or winds can lead to different results. Models can help us look ahead at many possibilities, test hypotheses, and compare scenarios, but they cannot make the future absolutely certain. If an idea requires very high reliability across the whole planet, that uncertainty becomes an ethical problem, not only a technical one. Some things appear only after long observation. Pinatubo helped humans learn a great deal about stratospheric aerosols, but a natural volcanic eruption is not the same as a long-running intervention program. An eruption comes and goes. The particle layer slowly thins and disappears. The planet responds for a period of time, then continues its rhythm. An artificial shade, if maintained, would become a prolonged condition, repeated again and again, dependent on human decisions, and shaped by politics, economics, technology, and conflict. Nature provides a short experiment. Humans could turn it into a long-term obligation. Those two things are not the same. A long-term shade could also change the color of the sky and alter the balance between direct light and diffuse light. Plants do not need only temperature. They need light for photosynthesis. Solar energy systems also depend on how light reaches the surface. Human beings live within rhythms of light and darkness, within the feeling of clear or hazy skies, within cultures shaped by sunlight, rain, seasons, and the color of the sky. An intervention in light is not only a number of watts per square meter, it touches the way the planet appears to the living beings beneath it. That change may be very small in each place, but if it lasts globally, it is no longer just a technical detail. Ozone, rain, clouds, temperature, light, oceans, politics, fairness, responsibility, and the psychology of delay, all of these things make artificial shade a much heavier idea than it first appears. At the beginning of the thought, there is only a small layer of particles reflecting the Sunday. Deeper in, there appears an entire planet with overlapping systems. Air is not only a place to put a layer of particles. Air is where life breathes, where rain forms, where chemistry protects the surface, where heat is transported, and where all nations depend together, even though they do not share power equally. A change in the sky never belongs only to the sky. Perhaps the hardest point lies in the appeal of the word temporary. A temporary measure sounds lighter than a permanent one. It can be described as a bridge, as extra time, as a temporary cover while the world reduces emissions. But human history contains many temporary things that lasted longer than expected. Once society depends on a system to keep temperature from rising too quickly, stopping it becomes difficult. Each year of continuation can make the next year harder to escape if the deeper cause has not been addressed. A temporary shade can become a long commitment across generations, a debt of light that those who come later must continue to pay. Humility before the atmosphere does not mean giving up understanding. It means knowing the difference between understanding and control. Humans understand why a sulfate layer after a volcano can soften sunlight. Humans can measure the haziness of the stratosphere. Humans can simulate part of the temperature response. But controlling the global climate would also require understanding how every region, every season, every atmospheric layer, every ecosystem, and every society responds. The distance between those two things is very large. A mature science is not a science that says yes to everything that can be done. It is a science that can see the limits of its own ability to act. Tiny dust particles in the atmosphere teach a two-sided lesson. The first side is wondrous. The small can touch the large. A single particle can change the direction of a ray of light. Countless particles can soften the light of an entire planet. The second side is more severe. The small can also carry consequences that are hard to see. A particle layer can change rainfall. A chemical reaction can affect the ozone layer. A cooling effect can mask the cause of heat retention. A decision made where power is concentrated can fall upon regions that were rarely asked for their consent. Smallness does not mean simplicity. If we look back at Pinatubo, the volcanic trace becomes clearer in another sense. That eruption did not only show that aerosols can cool temporarily, it also showed that the effect came and went on its own. The particle layer formed, spread outward, scattered light, softened the climate for a time, and then gradually thinned. Nature gave humans a brief view of the atmosphere's sensitivity. That view was not a simple invitation to recreate the phenomenon. It was more like a reminder that if a natural event is enough to make the global system respond, then any deliberate action in the same layer of atmosphere has to be considered with far greater caution. A sky can be dimmed, but responsibility cannot be dimmed along with it. When speaking about an artificial layer of reflective particles, every scientific question leads to an ethical one. Which models are reliable enough? What data is still missing? What risks can be accepted? Who gets to decide that level of risk? What rights do future generations have if they must continue maintaining a system they did not choose? How will harmed regions be protected? If the interests of one place conflict with those of another, who does the sky belong to? These questions do not take away the beauty of atmospheric science. They make that science more real, connected to the human world living beneath it. Earth can be imagined as a planet standing between two lessons. One lesson comes from light. Reducing part of the incoming light can make the surface gentler. The other lesson comes from life. Not every way of making things gentler is healthy, fair, or sustainable. Between those two lessons, humans have to move very slowly. We cannot pretend that aerosols have no power. We also cannot treat that power as an easy escape. A layer of shade can soften sunlight, but if that shade shifts rainfall, changes upper atmosphere chemistry, slows society's effort to reduce emissions, or places responsibility on the shoulders of future generations, the initial coolness carries too high a cost. Earth is not lacking in natural mechanisms of reflection. White clouds return light every day. Ice and snow brighten the polar regions. Sea salt, mineral dust, and natural particles take part in clouds. Volcanoes occasionally send particles into the upper atmosphere, then leave the sky after a time. These mechanisms have existed within the climate system over long stretches of time, though they too can create strong disturbances when they occur in extreme ways. Deliberate intervention in the upper atmosphere would not merely add another mechanism, it would add human intention to a place that connects every region of the planet. When that intention does not yet have enough understanding, enough fairness, or enough control over risk, caution is not born from fear. It is born from recognizing the scale of what is being touched. On a dusty, hazy day, people may see the sun as a pale disk behind a layer of gray-white air. That feeling is very different from a clear day after rain, when the light is stronger but the breath comes easier. Those two images are enough to remind us that less sunlight is not always better. A planet that is cooler at the surface but altered without enough understanding is not an image of safety. A screen of light cannot replace a healthy sky, a stable ocean, protected forests, reduced emissions, and a cleaner energy system. Shade only has meaning when it does not hide the difficult work that must be done on the ground. When sunlight passes through the atmosphere, every tiny particle can redirect that light a little. This is beautiful in a scientific sense. One small interaction, repeated countless times, creating a large effect. But that beauty does not grant a simple right to turn the sky into a tool. The more we understand tiny particles, the more we see that the atmosphere is a place of fragile connections. The more we see how Pinatubo produced temporary cooling, the more we see the difference between a natural event and a human decision. The more we see that a reflective particle layer can influence temperature, the more we must remember that climate is also rain, wind, ozone, oceans, forests, crops, health, and fairness among human beings. The safest shade for Earth is not an artificial haze, suspended high above that humans must maintain forever. It begins with things less dramatic but more certain. Reducing what makes the atmosphere hold heat for too long, protecting ecosystems that absorb carbon, keeping the air clearer for people to breathe, giving oceans and forests a better chance to stabilize, and keeping the sky from needing to be dimmed by harmful particles. These actions do not feel as fast as pulling a curtain. They are slower, harder, and demand deeper change. But that very difficulty is what touches the cause instead of only touching the light. Between the sun and earth, there is always a thin atmosphere. That layer is already wondrous enough, as it creates clouds, reflects sunlight, holds warmth, lets rain fall, carries wind, and allows life to breathe. When humans think about adding a deliberate layer of shade to that place, wonder must come with restraint. A planet should not be seen as a problem with only one variable. A sky should not be treated like a pane of glass that can be darkened without touching anything else. A civilization that understands how dust particles can cool the planet must also understand that the ability to do something is not the same as the wisdom to do it. Tiny dust particles have opened a deeper way of seeing Earth. They show that light can be redirected before it reaches the surface. They show that volcanoes can leave a trace in climate. They show that clouds, dust, smoke, sea salt, and sulfate all take part in the planet's thin shade. Then, when the idea of creating shade ourselves appears, those same tiny particles remind humans to slow down. Not every shade is protection. Not every cooling is healing. Not everything that can be modeled from nature should become a tool in human hands. In the thin atmosphere, embracing the living world, humility may be one of the deepest forms of understanding. Earth still turns beneath the light of the sun, not faster because humans have understood one more thing, and not slower because there is still so much they do not fully understand. On one half of the planet, daylight is moving across seas, forests, cities, and bands of white cloud. On the other half, darkness is falling over mountains, rivers, fields, and small homes. Between that light and darkness, the atmosphere still holds the living world in a layer almost impossibly thin, thin enough to appear from orbit as only a faint blue rim, yet important enough to hold warmth, make rain, carry winds far away, form clouds, and place every ray of sunlight into a delicate encounter before it reaches the surface. Within that atmosphere, tiny particles continue to drift. Some come from wave crests when the sea breaks into white foam. Some come from deserts when wind lifts mineral dust from dry ground. Some are born from fire, from smoke, from ash, from rare eruptions powerful enough to send material into the highest layers. Some appear from human activity, carrying the trace of fuels, industry, ships, cities, and the choices of a civilization living beneath one shared atmosphere. Each tiny particle has its own origin. Each meets light in its own way. Some scatter sunlight, some absorb energy, some become starting points for cloud droplets, some fall quickly in rain, some remain longer when carried into higher, more stable air. No particle creates climate by itself. No particle alone has enough power to cool the whole planet. But Earth is not made of solitary things. This planet is held in balance by the sum of countless small processes. A cloud returning light, a region of ice reflecting sunlight, an ocean absorbing heat, a forest breathing water vapor into the air, a salt particle helping a cloud droplet come into being, a sulfate particle high above redirecting a ray of light, a layer of greenhouse gas holding onto warmth escaping from the ground. Each process may seem small when seen alone, but when it unfolds across the whole planet, it becomes part of the slow breathing of climate. Tiny dust particles have opened a different way of seeing greatness. Usually, humans think of power through things that are easy to see. High mountains, wide oceans, large storms, erupting volcanoes, enormous glaciers, deserts stretching all the way to the horizon. But in the atmosphere, power sometimes lies in things that have no clear shape. A thin layer of particles does not cast a black shadow on the ground. A small change in brightness does not make everyone stop at once and notice. A little sunlight returned to space can pass through daily life almost unfelt. But thermometers, satellites, oceans, clouds, and the sky all have ways of recording those changes. What is almost invisible can still leave a trace when it lies in the right place where light must pass through. Pinatubo once showed this very clearly. An eruption on an island did not only leave ash around the mountain region, it also carried gases into the upper atmosphere, allowing tiny sulfate particles to form, spread outward, and soften sunlight on a large scale. That effect did not last forever. It did not heal the climate. It did not remove greenhouse gases from the sky. It only opened a rare window through which humans could see the sensitivity of Earth's system. As the particle layer gradually thinned, sunlight grew stronger again, while the lesson remained. The atmosphere can respond to very small changes in the flow of incoming energy. That lesson does not lead to easy confidence. It leads to caution. A particle-filled sky can weaken sunlight, but dirty air is not protection. A reflective layer can lower temperature in a narrow sense, but climate is not only temperature. An idea to dim the upper atmosphere may sound simple when it sits inside a few lines of theory, but the real atmosphere also contains rain, wind, clouds, ozone, oceans, seasons, forests, health, politics, responsibility, and regions that never share risk in the same way. A shade is precious only when the person standing beneath it is safe. For a planet, that is far more difficult than a gentle image of softened sunlight. Earth does not need humans to see the sky as a simple machine. This planet needs to be seen as a living system where everything is connected through paths that do not always appear right away. Light touches the sea and becomes water vapor. Water vapor rises and becomes cloud. Clouds reflect sunlight and soften the ocean surface. Dust helps cloud droplets form. Bright ice returns light. Dark surfaces hold more heat. Greenhouse gases hold on to part of the warmth. The ocean remembers heat longer than the air. Wind carries particles across many regions. Rain pulls particles down to the ground. A small change in one place can pass through many links before appearing somewhere else in another form. Perhaps the deepest beauty of the atmosphere lies in that fragile endurance. It is not as thick as the rocky crust. It is not as wide as the ocean. It is not as bright as the Sunday. But every breath, every cloud, every raindrop, every wind, every sunrise, and every quiet night on the ground takes place inside that thin layer. The atmosphere is not the empty space between us and outer space. It is where Earth meets the Sunday. It is where light is softened, held, returned, and divided into many paths. It is where tiny particles, unnamed in everyday life, take part in an exchange larger than any city or nation. When people think of dust, they often think of something to wipe away, something that gathers on a table, on a window, or on dry roads. But in the atmosphere, dust and small particles carry another meaning. They are traces of sea, land, fire, hot rock, burning forests, clouds, and even civilization. They show that Earth is not separated into isolated pieces. The ocean can send salt into the sky. The desert can send dust across the sea. A volcano can send gas into the stratosphere. A city can change the color of the sky. Things born at the surface can enter the light above, then return to influence the surface by making sunlight softer, clouds brighter, the air heavier, or the sky hazier. From those tiny particles, a quiet truth appears. Nothing in nature is truly too small when it belongs to a system large enough. A small water droplet contributes to a cloud. A salt particle contributes to a cloud droplet. A sulfate particle contributes to scattered light. A particle layer contributes to surface temperature for a time. A human choice contributes to the shared sky. No small part carries the whole responsibility, but every small part has a place in the wider network. The planet does not operate through isolated gestures. It operates through the resonance of countless very small gestures. That understanding can make humans less hurried. When we see a cooling effect, we do not need to immediately turn it into an escape route. When we see a layer of particles reflecting light, we do not need to forget the cost of particles in the air. When we see a volcano temporarily soften temperature, we do not need to call the volcano a climate savior. When we see clouds reflecting sunlight, we do not need to think clouds always cool in the same way. Each phenomenon is true within its own range. Each phenomenon must be placed inside the whole atmosphere, the whole flow of energy, and the whole life beneath it. Science does not make the world simpler. Science helps humans see that complexity more clearly without losing its beauty. Sunlight will continue coming to Earth in silence. Every day, 1/2 of the planet turns toward the sun and receives a new stream of energy. Clouds will continue returning part of that light. The sea will continue holding part of it. Ice will brighten when the cold season returns. Deserts will cast a golden brightness into the air. Forests will absorb sunlight to feed their leaves. Tiny particles will continue drifting through the sky, born from sea, land, fire, volcanoes, and humans. Some will scatter light, some will hold heat, some will disappear in rain. Some will travel very far before falling onto a place that never knew where they began. Beneath that atmosphere, humans will continue living ordinary days, opening windows, watching clouds, avoiding the sun, waiting for rain, taking a deep breath after a storm, seeing the horizon more clearly when the air is clean, gazing at the red of sunset without always knowing how many tiny particles are standing between their eyes and the Sunday. That ordinariness does not make the phenomenon less wondrous. It only shows that the greatest things about the planet are often hidden inside the most familiar moments. A softened sky, a white cloud, a streak of light on the sea, a deeper evening color after a volcano far from daily life. All of them belong to the same thin layer of air connecting humans to the Sunday. Earth's invisible shade is not a shade for humans to create at will. It is a sign of a sensitive planet where light, matter, and life are continually adjusting one another. Understanding that shade does not make the sky simpler. It makes the sky more worthy of respect. Each tiny particle in the air is no longer a meaningless detail. Each cloud is no longer only a white shape drifting past. Each sunset is no longer only a beautiful color at the end of the day. All of them are ways the atmosphere shows that it is working, filtering light, holding warmth, making rain, reflecting the sun, and protecting life through mechanisms that are delicate but profound. As the planet continues to turn, darkness and light will continue trading places across the surface. Places sinking into night will slowly cool. Places approaching dawn will receive new rays of sunlight. High above, tiny particles will still drift in air currents no one can see directly. Some particles will fall with rain. Some will fade through chemical reactions. Some will become part of a cloud. Some will quietly redirect a ray of light before disappearing from the sky. No sound accompanies these things. No large sign announces that part of the planet's energy has just been adjusted. There is only the atmosphere continuing its work, steady, subtle, and almost silent. Tiny dust particles can cool an entire planet under certain conditions, but the greater gift they leave behind is not the idea of a curtain against sunlight. That gift is a way of seeing Earth as a world held by countless small balances, seeing the atmosphere as a living layer, not an empty space, seeing light as a stream of energy that is always redistributed before becoming warmth, seeing smallness as part of greatness, and seeing human understanding as something that must walk with humility, because a planet sensitive enough to change because of particles almost impossible to see is also a planet that should not be treated like a simple problem. In the end, Earth is still a blue sphere, warmed by a star, sheltered by a thin atmosphere, covered by clouds, oceans, ice, forests, deserts, and cities that glow when night falls. Between that star and the surface, tiny particles still move quietly through the stream of light. They do not carry the grandeur of the cosmos. They do not have names in the memory of most people. They do not appear as large objects on a map, but in the silence of the atmosphere, they remind us that an entire world is sometimes shaped by things so light they are almost impossible to hold. And when we understand that, the sky above is no longer just a familiar stretch of blue. It becomes the fragile boundary where light, dust, clouds, and life together help this planet continue turning gently within the vast darkness of space.